afternoon, LastCon. Welcome to Small Language Models for Application Security Beyond ChatGPT. My name is Barrett. I'll be your guide today through the journey on the future of application security. I'm a full-stack security researcher with a passion for building security tools and solutions that increase the efficiency and happiness of my teams. I currently lead product security at Scale AI, where we focus on implementing security solutions for the ML ops lifecycle and ultimately improving the security of AI-backed products. Prior to this, I led detection engineering and incident response teams at both Segment and Twilio. In these roles, I gained my first experience in implementing machine learning algorithms and approaches to detect and prioritize security threats. Ever since then, I've been experimenting with solutions at the intersection of artificial intelligence and security. And the goal of this presentation today is to enable security teams to unlock cutting-edge capabilities and apply them to security challenges. To accomplish this, we'll cover some basics of language models, their recent history, and current capabilities. Next, we'll look at some of the common application design patterns emerging around LLMs and categorize them to better understand how language models are built. Next, we'll look at what models under 30 billion parameters can do for us. These are small language models. And take a look at some common language model apps, break down their functional composition, and then we'll show you how these can map to AppSec responsibilities. Finally, I'll share a couple demos and lessons learned around these use cases. And if time remains, I'll take some questions. Before I get started, a quick poll. So who here is responsible for threat modeling, security reviews, or addressing vulnerabilities? Awesome, that makes things easy. Who here has heard of large language models? Okay, how about small language models? That's what I thought. Have any of you used OpenAI prior to ChatGPT? Interesting. And how many of you are familiar with Hugging Face? Cool. And finally, who's attempted to deploy your own language models internally? Interesting, okay, cool, great, thanks for that. So for anyone who wasn't familiar, large language models, or more commonly large language models, are powerful AI algorithms that can analyze text and language, as the name implies. These models are trained on a massive corpus of data and tasks, allowing them to produce incredible results when applied to challenges typically handled by humans. Over the past 3 years or so, and more recently the last 12 months, the development of and evolution of these models has basically exploded. It's what we're kind of terming the AI summer. Prior to 2020, practical and production use of artificial intelligence within security teams was basically science fiction for all but the most well-funded organizations. And even then, those who did have access to artificial intelligence often found it unwieldy and challenging to deploy. The language models of this era often required an absurd amount of computing resources to perform even the simplest natural language processing tasks. And to make things even more challenging, deploying them generally required a data science background. I don't know about you guys, but I don't have that background. And I'm not a big math guy, so that was really a challenging period for me getting into this stuff. And needless to say, the security solutions that are built on top of these models at the time were far from reliable. And that's like partially because the people who are building them don't understand our use cases, and also partially because they're just so large and unwieldy in the first place. But in June of 2020, this all really changed with the release of OpenAI's ChatGPT. And while we had transformer architecture models before this point, it wasn't until the public and other engineers really got aware of this technology that it really started to boom, because we started applying it to our own use cases. For those who aren't aware, GPT-3 is a decoder-only transformer model of deep neural networks, which uses attention in place of previous reoccurrence, like older generation models did. And this allows the model to selectively focus on segments of its input and predict which is the most relevant to the actual user. Development of this new transformer model jump-started the development of similar models using the architecture. In the midst of a global pandemic, where many of us are trapped inside, and the unexpected availability of GPUs due to their major cryptocurrency platform or moving away from GPU-based mining, as the Ethereum merge, the next 3 years would see hundreds of models being developed, which brings us to 2023. This year has been especially interesting due to the release of OpenAI's GPT-4 and ChatGPT, as well as the beginning of the open source revolution led by the accidental leaking of Meta's LLaMa model. Since then, hundreds of models based on this transformer architecture and Meta's LLaMa have been released, allowing researchers and organizations the ability to experience artificial intelligence for themselves. And even more recently, Mosaic ML and Mistral AI respectively released the first open source models which could be used commercially. This is a game changer. You can now take these models, train them a little bit, and actually sell them back to your customers if you're a security company, for example. These new open source models have been found to perform comparably to the original GPT-3. And considering GPT-3 took millions of dollars to train and occupied 800 gigabytes of memory and utilizes 164 billion parameters, a model of only 7 billion parameters performing nearly equally is nothing short of an engineering miracle. In the next few slides, I'll go over what these models are able to do for us and get to some of the common types of language model apps. So, what can language models do for us? The language models of today, depending on how they were trained, are able to perform a number of different types of tasks. You can see the different types listed here. But first up is text generation, which we're, I think, all familiar with at this point. It represents the model's ability to use internal neural networks to generate coherent human language. Next, we have text summarization, where models are able to ingest large corpuses of text, extract key points, and generate a more concise result. So compressing some text down to a more concise version of itself. Question answering, where the model is able to we're able to provide answers to questions asked based on the data in its internal network and occasionally user input. And finally, classification. Models are able to determine if the provided data by the user falls into one category or the other. Say, for example, is this Twitter post offensive, right? Things like this. By combining the language model capabilities on the previous slide with traditional software engineering principles, a number of design patterns have emerged. These design patterns typically take the form of adapting AI to human roles in some capacity, and some popular examples include conversation apps, such as chatbots and personal assistants, the most popular of which is arguably ChatGPT. Next, we have our writing apps, leveraging the generative assimilative capabilities of the models, allowing end users to create creative writing and professional content. One such example is copy.ai, where you can make business copy, email copy, marketing copy using these methods. And lately, we're seeing the development of a new pattern where you have these process management and analysis support applications. And all of these applications are amazing. They have one thing in common, in my opinion, that essentially is an Achilles heel. Nearly all of them rely on commercial, large language models. And while this seems like an advantage at first, there are numerous issues related to data privacy, data sovereignty, and information security. When GPT-3 and later ChatGPT became popular, many organizations quickly had their data leaked almost overnight due to overeager employees using the models. But that being said, let's dive into understanding how these applications are composed by using the LLaMa maturity scale, and hopefully should allow us to build safer, more private alternatives to some of these application design patterns, and ultimately leverage them for sensitive use cases such as security. So the LLaMa rating scale is a scale we use internally to basically evaluate how complex an application is and what we should look at in terms of either securing it or deploying it. The scale is currently broken down into 5 levels. Level 1 being basic, which is basically a one-to-one interaction with the model. You have basically no short-term memory, so the model doesn't remember the last interaction you had with it. It's basically prompt in, response out. And the entire context passed to the model is used for that one-to-one interaction. At level 2, models gain extended context, and we see the chat design patterns start emerging. You have this limited short-term memory, which allows the model to remember its last few interactions up to a point. This is usually based on the maximum context window available to the model. Additionally, it allows the model to remain grounded because you have some previous context in your discussion, so it's less likely to hallucinate if you're nudging it along. We'll touch on this a bit more later. And the actors in these LLMAP systems tend to be now a human user, a system user, or a system prompt to give it some guidance, and of course, the language model's internal neural network. The data sources in this case are the user input, and of course, the model's internal neural network's training data, and the interaction style becomes multi-turn. So you're going back and forth with the model until it's able to give you the type of response you need. And as mentioned before, ChatGPT, most common example of this chat design pattern. At level 3, things get really interesting, and this is where I see a lot of the current design trending to within LM apps, where we're now using indexes to do a pattern called RAG, or Retrieval Augmented Generation. And it allows the language model to no longer have to rely on the data it was trained on. Due to the addition of retrieval indexes in the form of vector databases or traditional search clusters, models are able to augment their capabilities immensely and then almost completely eliminate hallucinations. So you can imagine passing in a complete corpus of what the model should use as rules, and will always reference those rules in its latter generations. So this leads to models having responses that are more truthful, more correct, and ideally safer for an end user to actually interact with. And due to how retrieval works, it's a multi-phase process. You can't pass an entire database worth of content into a model due to this limited input window. You basically chunk into smaller pieces, and that's what kicks off this multi-phase type of interaction with the model behind the scenes, even though this is typically invisible to the end user. Now, I mentioned there are 5 levels to this, right? And so far, we've touched on 3. And I'd like to mention that, for the most part, a lot of organizations right now are just scratching the surface of level 3. You don't really see it well commercialized. And level 4 is almost unheard of in production. But I want to just touch on one notable example of a level 3 application that we've developed at scale. It's a retrieval platform called Donovan that allows you to basically connect either things like Confluence, Google Drive, your Google Docs, whatever you want to your model as a retrieval index, such that you can ask questions in that corpus. We use this a lot internally in the security team to drop in all of our policy documentation, give this to our salespeople such that they don't have to come to security and ask questions. It's all already in the docs, and the model is basically following our best practices. But that being said, let's actually take a look at what level 3 entails, because things get really interesting at this tier because it's really experimental. And since there aren't too many commercial products, it kind of diverges in 2 directions, whereas the previous levels have been directly iterative. So it's, again, I mentioned it's split into 2 levels. We have level 4A and level 4B. Level 4A brings about language model-based agents, which we're just starting to scratch the surface on. Most of these aren't in a true production environment right now. And that is, models can interact on their own to some degree and solve problems for their user. So this introduces the addition of a goals manager or goal framework behind the scenes. And that basically breaks your single query down into either steps or instructions for the model that generates sub-prompts that either the core model or additional sub-models follow. So the actors in the system become the human user, our existing system prompts for guidance, which are basically always there from level 3 and up, our goals manager or goals framework, and obviously the language model's internal neural network. As with the previous level, we also have retrieval indexes here. So not only is the model able to go out, or the application able to go out and act on behalf of the user, it's also able to reference content that the user has provided ahead of time as guidance or a guidebook, right? And as with the previous level, the interaction style is multi-turn and multi-phase. So you can chat back and forth with this type of a model, and you can also have it occur in phases because we're using retrieval, and also the goal framework stepping through a list of goals until it reaches the end, right? So that becomes multi-phase. And we've recently seen the emergence of level 4A in ChatGPT, but it's not as direct as people would really think. They added recently a feature called Search with Bing. It's very experimental. Lots can go wrong there, and I'll touch on that later in the talk. But the model systematically does Bing searches until it finds the answer to the thing you were looking for. And behind the scenes, it's treating Bing as a retrieval index and treating your prompt as the source for that original goal breakdown. And when it finally breaks things down to goals, it's taking all those goals and searching them on Bing and then summarizing everything and bringing it back to the end user. So right now, I think ChatGPT is the only commercially or publicly accessible platform that I've seen do this at least a little bit. But we're definitely going to see more of this as time progresses. But with that said, let's jump into level 4B, since again I mentioned things are kind of diverging a bit here. Level 4B introduces multi-model consensus, where you have multiple models kind of acting together. Here you need an extensive short-term memory because the number of interactions you have, even in a single conversation, can be pretty extensive. Requires a large input size, so models that support more than the standard 2,000 tokens. And just to kind of break down what tokens are for language models, one token is about 3/4 of a word, right? So you can imagine you can get pages and pages of data into these things if you have a large input window. We have a new item getting added to our data sources in the form of an orchestrator. The goal of this orchestrator is to basically give work to all the submodels in this system and tell them how to actually operate. And once this orchestrator has gotten the results back from all of the submodels, it rolls those results back up and says, hey, user, here's your answer. So you can imagine this being used if you arrange models into teams or virtual teams, where you have one being the manager, one being the engineer potentially, and one being the designer, right? And they all have different goals, but they relate to the larger project. You can kick a prompt off this model such that it rolls up what the entire project plan would look like, because the submodels have their own individual goals being kicked off by the orchestrator. ChatGPT actually does this behind the scenes, and this is for GPT-4 specifically. Lots of people think GPT-4 is a single model, but it's actually many models behind the scenes, or like 3 models in a trench coat essentially is what you're really getting. Level 5, again, this is like unheard of. This doesn't really exist in a commercial sense yet, but models get long-term memory and start acting in true cohort systems. So taking that concept from level 4B, where you have small pods of actors, and scaling that out, right? So horizontally scaling that concept. The input size has to be immense because you're basically taking a huge chunk of data and dividing that across a number of different models. We have our orchestrator from the previous level, along with internal indexes, and we have this multi-turn, multi-phase interaction. But the difference here is now you have pods of models able to communicate with each other. So you have an orchestrator in each pod that talks to another pod and says, hey, did you finish either summarizing or whatever the goal of that other pod was? And then there's a grand orchestrator that rolls everything back up to the top. So you get the ability to basically coordinate models at a high level, but the resource usage and requirements of a system like this typically make it something that's out of the realm of consumer usage. And I'll kind of leave that there, right? One sec. All right, so those of you who are following along, congrats. We've reached the practical portion of the talk, and I'll try to slow down, but if I'm going too fast, please let me know. We'll get into real-world use cases for the model capabilities and design patterns and map the design patterns to some of those real-world cases using the rating scale we covered earlier. So I just want to share this quote from William Gibson real quick, because I think it really touches on how things are currently moving in the AI space. And that's: the future is already here, it's just not very evenly distributed. And the goal of this talk is to more evenly distribute that future and allow us to greatly improve application security, right? So to me, application security has always been about securing the software development lifecycle. So let's see how we can apply some of the concepts I discussed earlier to the actual software development lifecycle. So AppSec teams typically have the challenge of juggling security design reviews, threat modeling, code reviews, and vulnerability management. Each of these responsibilities requires us to read lengthy documentation, draw conclusions, follow up with developers, and provide recommendations. And so for those who've been paying attention, you'll notice these responsibilities basically map fairly well with the task capabilities of language models, which are summarization, closed QA, classification, and instruction following. And the natural alignment between our responsibilities and the capabilities of these models is why I first began this research. In the following slides, we'll see how we can leverage the capabilities of these models, mainly small language models, to improve the speed and accuracy of our security team, But please keep in mind that the goal is not to fully automate your jobs. That simply cannot be a thing at this point, but rather to assist you in completing them and reduce the time you spend doing painstaking tasks. So everything I'll describe going forward requires some level of human interaction or human in the loop somewhere in the process. And that's both to avoid the LLM top 10 vulnerability number 9, which is over-reliance on the model's output, because we do have to review and make sure these things are correct. Otherwise, terrible things can happen. You don't want a dev shipping something that's vulnerable that that had the model sign off on without any kind of review, right? Cool. So let's touch on how we can use models for security design review. Typically, hopefully you guys can see this, a development team provides some initial documentation, such as a software design document or product requirement document. The team then reviews the document and signs off with a rating of pass, fail, or review. A pass allows developers to continue to the next iteration of the design until a significant change occurs. However, in scenarios where they need to, or doesn't satisfy design requirements, we fail or say it's a review, and then the security team follows up and says, developer, change thing, go back to review. The review process ideally shouldn't take up much time, but when you consider how outnumbered most security teams are, these reviews can quickly pile up and clog up the works. Considering these challenges, let's think about what security design review really is and how we can plug in a language model and make the process more scalable. So whenever I'm thinking about whether or not I should use a language model, you can ask yourself this: who is prompting me, and should they be prompting a model instead, right? And if we apply this mapping back to the sequence diagram, we should be able to see how a language model can help here. In this case, the model is able to take over reviewing the user-submitted documents by reading this and summarizing the content, following the instructions provided in a review standard, and answering a few basic questions defined in the same review standard. It then provides a roll-up of the results to members of the security team for review. And although we only eliminated one step from this workflow, those of you who do lots of code review will understand this is the most time-consuming step. Design documents may be many pages long, highly complex, contain references to systems or concepts that more junior engineers might not be able to comprehend. And generally coupled with the volume of reviews that come in, it can make design review like a pretty heavy task for any security team. And if you're trying to shift left, it becomes almost impossible given the scale of it, right? And this is a relatively simple LLM app use case where we're able to quickly analyze documents, notify developers of gaps, and ideally while reducing the burden on your security team. So this is a really simple example, but I want you to keep these benefits in mind as we move on to the next example, which is basically a larger version of a security design review, the threat modeling session. Threat modeling can be considered a more advanced form of design review, like I mentioned. This is typically a collaborative process between developers, members of the security team, and occasionally other stakeholders. The threat models can be conducted synchronously or asynchronously, with teams providing guidelines and documentation ahead of time or bringing them to the meeting. But regardless of the approach, there's a heavy analysis burden placed on the security team. Additional design documents, when they're provided by these teams, just testing here. So fine? Okay, awesome. So additional design documents, when provided by these development teams, they might contain content that the security team, like I mentioned before, wasn't familiar with, and we kind of have to go through those and reason with them, is this system in line with our design standards, right? And due to the complexity of the process and the number of people involved, it typically requires a significant investment, both from the development teams themselves and our security team. Dev teams are often on tight schedules. They want the phase to move as quickly as possible, but security teams want things to ideally be secure. We're security teams. And address all the vulnerabilities up front, that way they don't reach production. The disconnect typically results in either short, light threat models that leave gaps, or lengthy threat models that block the pace of development. Striking the right balance between speed and quality requires parties involved to be on the same page and collectively understand the risks within this threat model. Due to the differences in levels and point of view, this process, like design reviews I just touched on, can be extremely difficult to scale. But let's look at it from a high-level perspective for how we can actually apply some of the concepts we saw earlier to the threat modeling process. So the existing process requires quite a bit of back and forth interaction between development teams and security, and a solid understanding of the implications of both design and mitigation decisions. This can be especially difficult in resource-constrained organizations. I don't know about you guys, but we don't have a one-to-one relationship between our engineers and our security team members. And it's a situation where you can be swamped even if you are proficient in threat modeling and design review. But luckily, we can reduce the number of interactions required by injecting a language model into the process. This way, we can use the same task capabilities from the previous design review example to delegate work to our language model. The model will analyze, provide documentation as before, read our threat modeling guidelines. And you'll hear me mention guidelines a lot here. If you produce a good documentation internally today, you can easily benefit from using language models. So that's another reason to have your junior folks produce documentation, because you can feed that back into a model. It makes everyone's life easier on the line, right? But yeah, I mentioned it goes through the guidelines. It will highlight the risks in the proposed system and come up with some mitigations before submitting them to the security team for review. And in this example, the model actually takes care of most of the heavy lifting, reducing the burden of your security team by order of magnitude. But to take things a step further, we can automate the process a bit more. By providing the model direct access to things like your security standards documentation and guidelines, this is like a retrieval type of setup, the model will use this documentation to follow your best practices and rely less on direct feedback from your security team. So you're going from a few interactions with your security team in the model to one or two, while still remaining accurate. Summarize the use case here. We can reduce the number of interactions between teams, automate the majority of document and diagram analysis. That's a big one for some people. Just a note on diagram analysis. If you currently do threat models with just images of your system, you might want to stop doing that. Use Mermaid.js Markdown to describe your document, because then the model can treat your design as text and still understand the flow of the design, making it a lot easier to actually slot these things in. So again, I'll harp on this a lot, but good data in gives you good results out, and if you don't do that data work up front, you're going to have a world of hurt, right? All right. So we've got some mitigations out of our model here, but let's touch on another aspect of AppSec responsibility, the dreaded code review. I have to do a number of these per week, and honestly, this is the whole reason I put this together. We have developers who won't see you for weeks, and then all of a sudden you have a PR with thousands of file changes, right? So on the code review. Like I mentioned, this one isn't too crazy, but merge after Wednesday, we get this on a Tuesday or something, and 24 files have changed, 758 lines of code have been added. I don't know about you, but I'm not going to read that, dude. It's going to be like, hey, looks good to me, stamp it. Let the vuln management team deal with it. Let the security operations team deal with it. But obviously not the best way to actually design software, right? Yeah, just like previous examples, look at the existing way we do code review and then see how we can slide in a model to help us out. So today, I'm right here. Yeah, we're going to assume that the developer first creates a new branch or repository. This isn't always the case. They could also take over for another developer, which introduces other issues. But next, they commit some code, possibly hundreds of times, and eventually open the pull request, either as a draft or one that's ready for review. Some CI checks occur, stack analysis workflows running against the PR. The dev team notifies some reviewers, usually within their own team, and sometimes include the security team. And I just want to note that development teams might have a good idea of when to include security, and a lot of that's actually our fault, because when we put security checks directly in repos, they assume that, hey, security checks ran on my code. I shouldn't need security to come review it. But as we all know, security checks on your repo aren't enough. We actually do have to do manual code review. But let's continue the assumption that they did ask us to review. And by this point, we're often taken by surprise. Feels kind of like a pop. It's like, hey, surprise, you have a huge PR to review. Do you know what to do here, right? Like, have you even seen this code base? A lot of us within security aren't actually developers, and that disconnect is like one of the issues that causes friction during code review or missed items. Needless to say, the huge number of changes can put a massive strain on the team. So let's look at how we can do code review in an AI-assisted way. You'll notice from the flows here, without having to go into too much detail, so I'm sure you can't see the actual wording, the majority of the interactions now occurring between the developer and the language model at a high level. And security is almost uninvolved at this point, right? And due to the fact that these recent language models are excellent at both generating and evaluating code, coupled with the basic capabilities of generation and summarization, it is now possible to improve the speed and accuracy of code review by providing a model context from the development process, such as commit messages, file diffs, a PR description. So again, another reason to have good data. Force your devs to put descriptions on PRs so a model can read the description and you don't have to go back and say, what does this PR actually do? We can potentially reduce the evaluation time to seconds instead of minutes or days and actually keep pace with the developers, which makes them happier, it makes us happier. In the new AI-assisted version of our code review, like I mentioned, the language model took care of most of the work, going back and forth, reading all the docs, commenting on things, and also keeping track of the commit messages, diffs, and more. Right? So the more context you have in your PRs, the higher quality that data is, again, the better result at the other end. Just to summarize, rapidly analyze massive amounts of code. They were designed to do this. They were trained to do this. Provide consistent review quality. Like if you have a junior engineer review a PR, you have a senior engineer, you typically get different results. So this gives you a consistent baseline that you can also use to improve the quality of your more junior engineers and hold your more senior engineers accountable, since we all slip every now and then. The other nice thing here is it can scale to handle the load of developers just spitting out PRs, right? Like we've all been at the end of the year whenever we have to launch new software, and teams are asking for reviews. We don't want to block their actual development process. We never want to be blockers in security. We'll get that bad reputation. So this allows us to scale the process without compromising on quality. And up until now, I haven't touched on any of the nuance of actually building LM apps. But to shed a little bit more light on this, I'll break down the code review app a little further and provide a recipe for building a similar solution. The next few slides will cover our build requirements, which model to use for certain tasks, prerequisites, and a recipe for applying the design to your own environment. So first, let's start with design requirements. We want this to integrate into existing development workflows. We don't want to take developers out of what they're used to doing and make them do something completely different, right? They're either not going to do it or not going to enjoy it. We also want to make sure that it produces a result at least as quickly as a human reviewer. If the process takes longer, why are we doing it, right? So a lot of people will slot in language models and not really understand why they're slotting them in other than just use AI for the sake of AI. We don't want to do that here. We want to make sure we're getting an actual benefit out of this integration. Additionally, we want to maintain data privacy and security by using open source models, such that we're not leaking our code to third-party model providers, such as OpenAI and others. And we want to also, obviously for a security team's sake, be able to audit the decisions made by our models, so keeping some log of the interaction that occurred between the model and the connected systems, as well as looking at, for example, if we have a review that came through, did a human go back and validate the result, or is it unchecked, right? So we know where the fault is there. So all of these requirements are actually sourced from both the development team and the security team, like kind of collectively in the ecosystem right now. You can kind of tell which items are developers first versus which ones are security, but we need both. We need all of these requirements to actually make it a workable solution. So next, let's get into level mapping our code review application to see exactly what we need to put together for it to work. Due to the fact that it takes in file diffs, commit messages, and status checks, we actually need extensive short-term memory. The extensive short-term memory and large input size are needed for within our application to deal again with the diffs. But this necessitates also an internal index to store the diffs from these files, the commit messages, and everything else in one record, such that when we pull it into our model, it's able to reason over the entire PR and have to do several retrievals behind the scenes, right? But that's only possible when you have a large enough context window to actually take in all of that content. Additionally, the fact that the PR commits can occur asynchronously, they don't all happen at once, it can be over many days. But the order does matter. We need to treat these as a event stream or a conversation. So that maps very well to the original level 2 design where we have a chat type application. But in this case, the chat isn't user facing, it's system facing. Basically, the chat is between the model and your GitHub or GitLab or whatever, right? So that event stream becomes your chat. Building on top of that, and given the requirements, we basically need a level 3 model level 3 app at minimum because we have a retrieval section we need to do, and we also need a section for interacting with the model back and forth and maintaining that session stream, that conversation stream. In this case, you can consider the session ID, the repo, and the PR number. So this is how you're going to break up what conversation is occurring and be able to manage a number of these at once, right? So we can scale with that. Next, I want to get into how we choose a model. Since we know our high-level requirements and that require a sizable input window, and we're dealing primarily with code, I had basically 2 options for language models to use for this. Mosaic ML's MPT7B with an 8K context, or Hugging Face's Zephyr 7B, which is based on the recently released Mistral 7B model. I just want to note, like, I've had to rewrite this talk like 13 times due to the pace of changes in the AI industry, but this is currently my top 2 for actually deploying this stuff internally. So our chosen model, should be somewhat obvious, I hope, was MPT7B. And this was released back in March, and the Mistral model was released this month. But what I found through testing was that the Mosaic model was generally better all around and excelled at code, even though it was only okay at retrieval tasks. The 8K context window made it amazing for giving it prompt-tuned instructions. In this case, prompt tuning is in between your prompt engineering and your classic fine-tuning where you have to fully retrain a model. Instead, you give it all the instructions you can, using up a good portion of that 8K context to say, do this thing. That way you don't have to go back and retrain the model, and that allows you to dynamically update how your models behave without spending hundreds of thousands of dollars retraining or hours and hours and getting the resources to do this. I just want to note that in terms of model sizing, to train a model that takes up 13 gigs of video memory usually requires an order of magnitude higher than that. And I don't know about you, but I can't find a video card that has 140 gigabytes of memory, at least not in my budget, right? So using ones with large context, despite their small size, can give you a nice middle ground to actually achieving good results. All right, so before I actually hop over to the recipe here, or the ingredients, I should say, one more thing I wanted to mention about these 2 models. These are the ones that are commercially available for people to use outside of just hobby type usage. So if you want to build a product around it, you actually can. Question?
How do you measure these things?
Great question. How do I measure them? So there are benchmarks that have been released, but a lot of these benchmarks are subjective because they weren't based on security use cases. They're based on general language use cases. So I measure these through actually using them over the past, say, like 9 or 10 months internally, right? And so how often do they give us the result that we didn't want in a review versus the one that actually our security team would have used? And we take those examples back out and put into that large system prompt, like I mentioned, such that they're nudged in the right direction. Thanks for the question. But yeah, moving on to the ingredients, the other parts of the system we'll need other than the model, since you consider the model the core, but we're going to build a level 3 application around it. The ingredients are, again, our small language model, a server to host this, a CI webhook host. This can be serverless. Anyone who's done any kind of GitHub Actions or CI automation should be familiar with that, so I won't really dive in there. An orchestration host. This is like a workflow manager, such as AWS Step Functions, N8N, or Temporal. A retrieval index host. You can go a couple different directions here. either using a vector database, which is a bit more complex, or Elasticsearch, which I really like to use in this case. It's simple to deploy and performs amazingly well when paired with the model. But here you can also use things like BigQuery and other available databases in its place. Next, we have our system prompts templates that we use to do basic code review, file diff guidelines, and status check guidelines. So the rules we give models when interacting with certain parts of our actual system. Next, we have our model configuration. So how do you want to set this model up to actually work within your application? Like I mentioned before, the MPT7 model is an 8K context, but I don't always use all 8K of that context. And the reason is when you set it that high, the model has to always consider that volume of information and actually performs more slowly. So the smaller you can get that context window set, you'll have faster tokens per second or faster response rate back from the model. And I typically allocate the token capacity in like a 4:2:2 ratio. So like half of the total context is for system prompts, a quarter of that is for the user input, and then the last quarter is for some usage-specific additional context. So if you're doing a file diff, you might say, this is a file diff, and we have this criteria kind of going along with it, where in the main system context, you are a bot that does threat modeling or code review or whatever else, like the cornerstone would be in that the half of the total context. Next, I want to touch on temperature. This is a setting within these models that basically adjusts how variable the output will be. And ideally, it should be set as low as possible for production use cases because you don't want it going off and like writing you poetry, right? You want this thing to be as on the rails as possible if we're going to use it in production. So set temp to 0.1. This works really well with the MPT7 model. Not as well with certain others because they do have a finer grade of what that temperature looks like. Time, okay. All right, so to get the best results of the model we chose, we need to design our inference system to actually handle these requirements, right? The MPT7 models and 7 billion parameter models in general consume 13 gigabytes on disk, 13 gigabytes of system memory, and up to 20 gigabytes of GPU memory at inference time. And due to the way these models are loaded, first being copied to disk, and then to system memory, and then into GPU memory, it's actually necessary to have a server that has more system memory than it does GPU memory. This is like a major pitfall of a lot of these designs when people try to roll this out, because most of the cloud offerings don't give you that split because they were focused on a previous generation of machine learning where you didn't need this massive amount of system memory to do that initial load, right? And just for some additional guidance here or like reference, a 30 billion parameter model takes up 60 gigs. A 70 billion parameter model takes up 140 gigs. And that's just on disk and in memory when they're loaded. When they're running, they take up about a third more than that, right? So again, one of the reasons that I trended towards smaller language models, there literally aren't systems that we can use to actually run them otherwise, right? Once you go above, say, 30 billion parameters. Okay, so another thing I want to touch on here is the retrieval index system. This is Elasticsearch. You typically have these in clusters. Here you don't need too many resources because you're really just dealing with text. It's not like a logging or scene platform where you have gigs and gigs of text, but you still need enough headroom such that it's performant. And here I use basically the smallest offering, 4 cores, 8 gigabytes, and 40 gigs of storage per node, because actually we don't even need to retain any of the file diffs or PR context for a long period of time. They life cycle out. Cool. So gave some core components of the actual design. We have our interface layer, which is a Gradio. This is an experiment interface now owned by the team at Hugging Face, and basically allows you to wrap any language model in 3 lines of code and actually serve that as both a web app with a GUI and an API, which is really convenient. Next, we have some core libraries you're going to want to be familiar with. PyTorch being the most necessary here. I just want to mention that there are 2 current branches of PyTorch, version 1 and version 2. Version 2 has been heavily optimized, but most projects are pinned at version 1. Leveraging version 2 typically gives you a 33% speed up without using any more memory or anything like that, and also allows you to, in certain circumstances, directly load models from disk into GPU memory, bypassing the system memory, right? But this is only true when you couple it with safe tensors, which are an optimized version of the model's core files. Like they're exported in different formats, such that there's no executable code, no risk of having malware run in your model's actual file. And just keeping in mind that these models are actually pickled Python code, so you can have model malware. It's a thing. Use safe tensors. Next here is Hugging Face Transformers. A few of you are familiar with this, but it's probably the now de facto library to do anything with modern natural language processing. And also it can give you, a model interface in 3 lines of code. Really, really easy to implement. Finally, I just want to touch on some general system things. Python projects have been around forever. A lot of people use virtual environments, but I really like how compostable poetry makes designing these projects. You get to include any of your system libraries, pin versions on model-specific things, and basically have something that's repeatable that you can run in a container or as a microservice if you want to go that route. As the operating system that actually runs the app, I recommend Lambda Stack. They basically roll in all of your dependencies around NVIDIA libraries, drivers, everything into one clean, nice package, and it keeps itself updated over time. So you don't have to go back and say, oh, my PyTorch implementation broke because my driver version is now different than the version required by the actual library, right? So highly recommend that if you don't want headaches. Yeah, let's go on to the recipe real quick here, make sure I'm leaving enough time for questions. Yes, we install our Lambda Stack, start a new Poetry Python project. We create an inference pipeline using Hugging Face. Again, this is 3 lines of code, like literally 3 lines of code. We add LLaMa index, which I haven't really touched on just yet. That allows you to chunk documents into sizable pieces that a model can digest. And this is what powers a retrieval system. Next, we wrap the model in a Gradio interface to easily provide an API and a web GUI for either administrative purposes or troubleshooting. But just a note on Gradio, since this is something that's used pretty much ubiquitously, and it does offer the predict and API endpoints, the GUI and the API are on the same route. So I really recommend putting a reverse proxy in front of that to only serve one or the other. Otherwise, you can get devs basically playing with your model's backend, and you don't typically want that. Finally, we deploy a webhook, your classic CI webhook, to call this Gradio API when a new PR is ready. So again, like I mentioned, things have been changing pretty rapidly. So next week, I'll be providing one code sample of this actual app, but more detailed descriptions around actually building this recipe out and share the repo. But that being said, let's dive into a little demo, right? Actually, first here, let me show you guys this diagram. Hopefully this loads. Come on. Will it load? Yes. Okay, so here's our new flow with everything kind of built in through a level 3 app. So I'll start from where the CI webhook kicks off so you guys can see the flow of that. But the the CI webhook receives a call from the PR. The code review begins based on the branch and the repo name. Again, repo name, branch name. Confirms it back to the app. And then the app is what actually goes and retrieves any supporting documentation from, in this case, Elasticsearch. And at the same time, it sends over one of our system prompts with the criteria and guidelines as the head of that actual prompt. And says, hey, go review this PR. The search is executed based on the PR number, since we're actually taking in some of the details around the PR, such as our file diffs, commit messages, et cetera, in our retrieval index. These diffs are the results are chunked back to the LLM app using LLaMa index and checked against neural network. And then that's returned back to the actual application as a short summary and verdict, which then bumps it back to our security team for review. So pretty straightforward. But like I mentioned, I'll share a repo with the actual code for this, as well as like a proper architecture diagram. It's a little easier to read. And let me switch over here to show you guys the actual front end or administrative interface of this app. I'm kind of using that retrieval pattern. Okay. It's the same diagram there. So this is a non-interactive example. It shows my prompt here. I always want to tell it the source of the data, because a lot of the times when you look at the training data that went into these models, they're structured like this. So if you're ever curious how to use a model properly, actually go read its either the training code or see the data sets it was trained on, because the examples will really guide the types of prompts you should make and use with this model. And additionally, you can also know terms you shouldn't use in your prompts that would throw the model off base. So I was looking at the tokens file for the model to see exactly what things are stop tokens, special keywords, et cetera, that you should avoid. And those tend to come up in code naturally, so it's something you want to know ahead of time. So here we ask it to provide a summary of the actions taken in this pull request and review for security concerns. We have some guidelines. The security team is only concerned with changes that impact authentication, authorization, or data security. And then the output format should be a short summary with verdict, pass, fail, or review, which would get sent to your security team. And as you see, the data source here is one of my repos. You can basically put that in on this interface, and it should go to the repo and actually pull back some context. So that's not interactive at a high level. I think I have time to show you the semi-interactive, actually, yeah, this is a real PR now internally that we had to review. Something goes across a public repo, so it's totally fine to show you guys this. This is open source. But there are some security concerns here, and the model will go through and actually use this PR review. If you take a look at how long this is actually taking, I don't know about you, but that's faster than I am. I've been doing this a while. We'll actually go through and do the review, summarize everything in the PR, and give you a result back. So like I mentioned, Gradio has a GUI and an API. I'm showing you the GUI here to basically illustrate this, but this would happen behind the scenes between the webhook, the user, and like the post back to your security team, wherever they are, whether it's Slack or directly on the PR or wherever else. Cool. And that brings me to questions. Happy to show you guys an interactive live demo, but I think I'll take a few questions since time is now running short. Awesome. You in the back there.
Which AI image generator did you use for your content?
I love how this is always the first question whenever there's like AI generated content. This is DALL-E 3 in this case.
Cool.
Yeah. Other questions? Yeah.
How would you persuade management that really wants to go hard on using OpenAI tools to look into something more private?
Okay, so there are two ways to approach this, right? Your spend on OpenAI per year is one thing to look at. I've seen people spend hundreds of thousands of dollars a month to run models, run inference through OpenAI, right? Cost is a big one. So when I mentioned the difference between the previous generation of cloud-based AI systems and the current generation, you find that you're unable to get enough system memory to satisfy your needs with the GPU memory almost ever without paying about, at minimum, like $700 a month, right? Something crazy. But you spend $1,500, $2,000 once, and you have a system that can do inference for you at this scale for the rest of your ownership of that device. And since these models are open source, you can cache them, modify them. You don't lose access to that. You also don't have OpenAI changing the model underneath your feet without you knowing, right? And it's probably too late to say this at this point, but the views expressed here are not from any current, previous, or future employer, and they're also not the views of ChatGPT, right?
So do you have documentation for all the AI DevSecOps things?
Yes, so I'll share that basically next week, because again, like things change so quickly that I cannot share the raw code right now. There are like cursed comments in that code, right? So some cleanup needs to happen, but this will all be shared in detail.
You plan to open source?
Oh, this absolutely, yeah. This is open sourceable. There's nothing here that isn't something you can pick up and do today. Like I mentioned, 3 lines of code will get you to the point where you can do inference against these models. The total retrieval system was about 100 lines of code, and that's only because I gave it variants in terms of where it could pull context from, like you probably saw on the slide before. It could read Google, Wikipedia, get supporting data from anywhere to better understand something that your internal team might not well understand, right?
Do you have any estimates on the time saved versus the cost of actually running it?
Rough estimates. Since we're a pretty small team, I would say that this is just being optimistic, that I've saved about 80% of the time I would spend on design reviews or threat models just through using this. And getting that time back allows me to do research, get to know my development teams better, and also like improve the quality of these types of services, because I get the time to actually interact with human beings since the models are doing a lot of that heavy lifting.
You have to productize.
Yeah, definitely can't do that, but thank you.
What's the hardware cost for?
What's that?
Hardware cost for?
Hardware costs. So as far as hardware costs, I recommend checking out Lambda Labs to get some guidance on what baseline hardware to build something like this looks like. Since this is always going to change due to GPU prices and prices going up and down, new boards being released, etc. But I think like going through Lambda Labs and looking at their desktop offering is a good way to kind of price out what the inference system might look like, and keeping in mind the requirements grid that I mentioned before. But I kind of went overboard when I built mine, so I don't recommend getting like 256 gigs of system memory and 12 terabytes of storage or anything like that. But you can probably get away with spending about $3,000 on something like this using a consumer grade GPU like a RTX 3090 or something like this. Cool. Any more questions? Yep.
How long did it take for you to build up the system? Did you do by yourself or you have your?
So realistically, to build everything, it took like a weekend. But to actually like build out the project, it was many, many months of iteration, right? So using all the different models that have come out, seeing where they fail, seeing if it makes more sense to spend the time to truly fine tune it, or whether or not I can convince a model to behave a certain way by editing the conversation I had with it, which is prompt tuning in this case, to nudge in the right direction. Thank you. Any other questions?
Can you share all the models that you tried rather than just the top 2?
Yeah, so there are about 7 that I looked at. And for the most part, the gap between 1 and 2 and the rest was so vast that I really only recommend using these 2 for open source use cases. Like even with the base LLaMa models or the base MPT model, like base Mistral model, their lack of basic fine tuning makes them very hard to use without putting in a lot of work. And especially when you have a limited context window, as many of these models do, you're not able to actually even prompt tune them in the right direction. So that MPT7 with 8K context is unique in that sense. It's a small model that can take in a massive amount of input such that you can guide it in the right direction.
Where did you host the models actually?
So these models were hosted on a physical machine, right? Because I kind of mentioned using the cloud offerings, it tends to be pretty crazy, but you can obviously offload data storage to things like S3 and stream in the actual model files yourself and run them that way, as opposed to storing them on a drive locally. 2 minutes? Any other questions?
What are typical bypasses? Because when you do this automated way, there are multiple loops in the code, and so what you observe, then you tune your model, right?
Yeah, so I mentioned workflow engines earlier, but I didn't really touch on their usage here. But that's where the workflow engines come in. Every single step of that workflow basically has an audit output as well as a lever that an engineer on my team can pull to basically say, do one thing either the same or different and kind of make some adjustments, sometimes in real time. Like if you see that this is a file diff heavy PR versus a comment heavy PR, you can actually switch the model downstream and say, I actually want to use the Zephyr model from Hugging Face instead of the MPT model such that it handles a certain condition better. And for future work, I'll probably use some of these models in parallel or in tandem because they're small enough to actually be run on some of these larger GPUs and have multiple models on the same GPU without any performance loss. Yep.
So we've been talking about the small language model. How small?
How small? Okay. So I think anything below 30 billion parameters is considered small, but at some point, basically next year, anything we thought was large today will eventually be small anyway. So long term, they're all going to be small language models. I think assigning size to any kind of technology is usually hubris, as we tend to go through Moore's law, right? But yeah, 7 billion parameters is where I consider small. There are smaller ones, but they don't perform nearly as well. There are things like mini LM, and those are 100 megs of disk space, but they really don't do the job well enough to actually be used in production.
So for example, you mentioned about, we have to run out of
Sure. One more?
And we're up at time.
Okay. You can see me later. Yeah.
Thank
you.
you very much indeed.